Alright, and for lesson 2, we're going to use what we just learned about manipulating reactions in K to figure out how to do the equilibrium constant for a reaction that is the sum of a bunch of other reactions. And we're going to work to figure out equilibria when the equilibrium concentrations are not explicitly given, and we're going to learn about heterogeneous equilibria as well. So these are some examples that we're going to do by the time this particular lesson is done. So now we're going to try to figure out if you add two reactions, what's the relationship between the equilibrium constant of the reactions that you're adding together and the sum reaction. So let's go right to an example. So I've got, I'm going to be calling here reaction 1, which is molecular nitrogen and molecular oxygen forming two nitric monoxides or nitrogen monoxides. The equilibrium constant for that reaction, hopefully you're getting good at writing these, it's just going to be the concentration of NO squared divided by the concentration of N2 divided by the concentration of O2. And here's a second reaction, which I will call, surprisingly enough, R2. And it is two nitric oxide molecules reacting with oxygen to form two nitrogen dioxide molecules. And that equilibrium constant should just be the concentration of NO2 squared divided by the concentration of NO squared divided by the concentration of O2. And now, this is R3. And the idea here is that hopefully you can see this, that R1 plus R2 is equal to R3. And the question is, what's the relationship between Kc1, Kc2, and Kc3? Is Kc3 the sum of the of Kc1 and Kc2, or is it something else? And the easiest way to figure this out is just basically to add the reactions, which will A, prove that R3 is in fact the sum of R1 and R2, and that might give you some insight as to what the rule is for adding reactions and their subsequent new equilibrium constants. And so let's just add it together. So we've got N2 gas plus O2 gas plus 2 nitric oxides, also gas, and another O2 gas. And I am purposely not combining the oxygens yet. And now we've got 2 NO gas as one of the products and 2 NO2 gas as the other product. And if you just cancel out the nitrogen monoxides here, you can see that this is in fact, that R3 is in fact the sum of R2 and R1. So now let's construct the equilibrium constant for this sum reaction. So this is going to be, in fact, Kc3. And let's just do it like we know how to do. Take the concentration of the products. So we've got NO2 and then raise them to their coefficient powers. So we've got NO squared and then we've got NO2 squared. And we will be dividing by N2 to the first power, O2 to the first power, and finally NO to the first power as well. I'm sorry, to the second power. Now, what do we find here? Let me switch colors here. And I'm missing something here. Oh, I need one more oxygen. And now, hopefully you can see the answer. Okay. If I do something like this. So what do we have here? We have NO squared divided by N2 divided by O2, which happens to be Kc1. And over here on the other side, we've got NO2 squared divided by NO squared divided by O2, and that happens to be equal to Kc2. So this expression is the product of the reactions. So the rule here is add reactions. If you add reactions, you're going to multiply the equilibrium constants for it. And just to take this to its logical conclusion here, if we do actually cancel out the nitrogen oxides, what you get is NO squared N2 and O2. My apologies, this is NO2 squared, which means I goofed here. Those are the ones that cancel. All right, which is, and then here, this is also what you would have written down if you would have just seen R3 all by itself. And again, this is the big thing. If you're adding reactions, you're multiplying the K. If you're subtracting reactions, you're dividing the Ks. So now we've got 3 manipulations. So we know that if you double a reaction or multiply a reaction, you raise the K to that particular power. If you reverse a reaction, you invert K. And now if you add a reaction, the equilibrium constant for the sum reaction is the product of the equilibrium constants for the individual reactions. So with that in mind, to test yourself, I've got an extra example for you. And here's the example. So I'm going to get you started with a couple of things here. Obviously, maybe we call this one R1, which makes this one Kc1 by extension, R2, which makes this Kc2 by extension. And this one is our target, and this will be reaction 3, and equal to Kc3, and our goal is to figure out what that is numerically. And with R1 and R2, we should be able to manipulate those to get R3, which means we should be able to manipulate these 2 equilibrium constants to get Kc3 as well. So let's see what that manipulation might be. So look for something that sticks out. Namely, one of them is the NOBr. So we need 1 mole of NOBr as a product. It is only present in R2. It is a product of R2 and 1 mole of it specifically, so probably you're going to leave this one as is. Now, what else do we need? So it turns out, if you look at it, that we need N2 and O2 as reactants. N2 and O2 are only present in R1, and they are products of R1. So this means that we will need to flip R1. And also, to get the stoichiometry to work, we're going to need to divide everything by 2, because in R3, it's a half mole of N2 and a half mole of O2. So our proposition is that R3 is equal to R negative R1 over 2 plus R2. And let's try that. So let's get, so that means here, if we want to flip and divide by that, what we're going to end up with is 1/2 of an N2 gas plus 1/2 O2 gas gives you NO. And remember that this is negative R1 over 2. So let's add those together. So we've got our 1/2 N2 and 1/2 O2 plus, and then we're doing the contribution from R2, which is going to be the NO and the 1/2 bromine. And the products will be 1 mole of NO and 1 mole of NOBr. And if we look for cancellation, which is basically the nitrogen monoxide, we do in fact get 1/2 N2 gas plus 1/2 of O2 gas plus 1/2 of bromine, also a gas, and that's going to give us 1 mole of NOBr, which is in fact R3, so our proposed manipulation worked. So now we need to figure out what to do with the equilibrium constants. So R1 we flipped and divided by 2, which means that we need to invert KC1, and since we halved the reaction, we take the square root of 1 over KC1 and then multiply it by KC2, because we didn't modify KC2 at all. So this is going to be, and if you work out that math, you should get 9.0 times 10 to the 8th. And again, so if you can do this type of manipulation, you will be fine for the exam. This is about as complicated as they get. But just again, remember the 3 rules. Add reactions, multiply the equilibrium constants, double it, half it, raise it to that power, whatever the multiplier was. And if you are adding reactions together, you multiply the equilibrium constants together.